Welcome back. So, in today's video lecture, we will look at what is known as Washburn equation. Okay, if you want to measure the contact angle of, let's say, bulk powders, especially porous material, we can use this approach, to determine the contact angle, right? So, remember when we derived the Young-Dupre equation, we made several assumptions, right? One of the assumptions we made was no absorbing of liquid by the surface, right? So if the surface is smooth and no imbibing in nature, then we can very well apply the Young-Dupre equation. But what if we have to deal with a porous material, okay? Bulk powder, which will absorb a certain amount of liquid into it. In such case, what kind of equation we can use, if not Young-Dupre? So that is the question that we are addressing today. So in this using this equation, you can measure the dynamic contact angle, okay, of any given porous material, okay, as a function of time. Let's begin. Yeah. So as I mentioned, we can use this capillary penetration method if you want to understand the contact angle measurements, right, of porous material. The approach is going to be very simple. So one would have to plug this porous material into the capillary tube, okay, and then this capillary tube attached with the microbalance can be carefully placed such that it touches the liquid, right? So then what will happen is this liquid molecule will be penetrated inside the porous channels, right? So these porous channels will consist of several porous channels. They will be interconnected three-dimensional network channels. Okay, through these channels, these water molecules will be absorbed by this porous material, right? So the approach is you can measure the mass of the uptake, the liquid uptake, okay, mass of the liquid which is being absorbed by the solid, right? And then by knowing the mass of that liquid, can we measure the contact angle, okay? So this approach is going to be the dynamic approach in which you will have to record the contact angle as a function of time, okay? Right. So this is what we are going to use, and our very first equation is going to be, Darcy-Weisbach equation. So that is something we will see shortly. So you will obtain the equation of this form, okay. While deriving, we will have to use this relation, capillary rise. Using the capillary rise method, the pressure, the delta P that we developed for the capillarity, using the capillarity approach, and then we'll try to see how we can develop a simple expression as a function of time, right? Right. So you can ask, where is this approach going to be really helpful? It is very important to know the wetting nature of the solid, especially when you deal with the operation like granulation, pelletization. Sometimes if you deal with coating of tablets in pharmaceutical industries, the wetting or three-phase contact angle or contact angle of the solid, the dry powder with the given liquid is very important, right? So one would use this approach in these applications, right? So let's try to understand the the derivation part of the Washburn equation. So Washburn equation, our approach starts with the simple fluid flow through the conduit or pipe. Okay, so our starting equation is going to be the Darcy-Weisbach equation. Okay, for any for any flow through the conduit or pipe. Okay, so in this equation, when we look at the this equation, you see that there is something called the friction factor. So we are going to assume a laminar flow, okay, because the flow is going to be inside the porous channels, through the porous channels. So it is safe to assume a laminar flow. So for laminar flow, we know this relation, that is friction factor is going to be 16 by Reynolds number, so which can be expressed in this form as well. Now, when we substitute this relation into this equation, we will get something like this, 32 mu L into U by D square, right? Because they are going to substitute in place of F, friction factor, they are going to substitute this the factor into this equation, right? And for brevity, we are going to call this the dimension L as denote L as H, because we're talking about the fluid, flow of liquid through the capillary tube, okay, suspended, right? So in this way, we can denote L as H for convenient, okay? So in that case, one would obtain the equation which is popularly known as Hagen-Poiseuille equation. Hagen-Poiseuille equation. This is we often this equation is quite familiar to all of us, right? Right. So from here, how do we depart from here? Okay, so let's write this equation. We know delta P is nothing but 32 mu into H into U divided by D square. We can write this equation in terms of U, which is nothing but delta P, nothing but delta P into D square, okay, divided by, right, 32 into mu into H, right? So we can actually write this D as in terms of radius, capillary radius. One would write this as 2 into R square divided by 32 into mu into H, right? All right. So remember, we're talking about not one radius of capillary tube. If you look at this, the capillary tube, you will have the porous bed. In this, you will have n number of cylindrical tube, right? You can say that these porous channels, as if you treat these porous channels as cylindrical tube, one would have to consider n number of cylindrical tube. In that case, some cylindrical tube may be very small, some may be very larger. So one has to use the statistical average rather than the capillary radius itself, right? So in such case, we can say that, okay, divided by 32 into mu into H, right? All right. So we can also express this in terms of volumetric flow rate, which is very convenient for us. So we can simply multiply both the side by area. Okay. In that case, one would get delta P 4 R gamma square divided by 32 into mu into h itself. Okay, all right. So since this is volumetric flow rate, I can use this as dV by dt, change in volume with respect to change in time. All right, and then I can use this as delta P 4 R gamma square divided by 32 into mu into h. Okay. So in this way, you can see that I can connect these two equations. Now I have delta dV on the left hand side. Then I will take this time derivative on the right hand side. Then I will simply have dt. Okay. Now this dV I can write as again area into h, right? Area into dh. Okay, right? Then I can simply write this as delta P into 4R square. I think when we multiply this both sides by area, we have to multiply here as well, which we missed. Kindly correct that, right? Okay. So you will simply have, this will be 4 R power 4 and into pi. Okay, into pi, and here also you have pi r square, right? Yeah. Right. So you will have 4 R power 4 into pi divided by 32 into mu into h, and then dt you have. So you can cancel pi r power square. This you can easily cancel out. So you will have r power square over there. Then if you bring this h here, you will have h into dh, okay, which is nothing but delta p into 4 r power square, okay, into t divided by 32 into mu into 32 mu. Okay, all right. So this I can write as h square by 2, which is nothing but delta p into 4 r power square into t divided by 32 into mu. So yeah, all right. So h square. So now I want to expand this delta p for capillarity. We know the capillary rise, right, through capillary tube. We can write this delta p as 2 gamma Lg cos theta, okay, into 8, right? This is going to be 8 r power square into t divided by 32 into mu into r bar. Okay, so this is what we have. So this will be 2, right? So h square is nothing but gamma Lg cos theta. You have simply r bar only into t divided by 2 mu. So this is my equation, okay, in terms of h, right? This is going to be my equation in terms of h. But what is going to be more useful for me is in terms of mass of liquid, so that I can directly calculate the mass using the microbalance, right? So that is going to be my approach now. So how I can do that is, I know mass is nothing but h into rho into s. So I know mass square is nothing but rho s h square or rho s square into h square. Okay, so we have this equation already, h square. So if I multiply both the side by rho s square, then I can simply substitute that as mass square, right? So that is what we are going to do now. So gamma Lg rho S square cos theta into R bar into T divided by 2 mu. This is my new equation. All I need to do is, this is going to be my mass square, okay? This is going to be my mass square. So I have gamma Lg cos theta rho S square into R bar, I'm sorry, this will not be R bar square, or you can correct this. Yeah. R bar into T, okay, divided by 2 mu. So we can write this equation in terms of cos theta, which is nothing but m square, okay, into 2 mu, all right, divided by gamma Lg rho S square into R bar into T, right? So you can see that this equation is in terms of T, which is nothing but dynamic Conet angle, right? So one step further, it is very useful for us to keep the what is known as the porosity in the equation, so that if you know the porosity, you can directly measure. So porosity is defined as void volume by total volume, or you can also say, the cross-sectional area, which is nothing but S by projected area, right? So this will give me the porosity, right? So if I substitute this over here, I can simply get cos theta as m square into 2 mu divided by, okay, gamma Lg into the rho S square is going to be my porosity multiplied by AP square, okay, into R bar into T. So if you look at this equation, so if you know the R bar, which is the statistical average of capillary radius and different function of time, as a function of time, you can actually get the dynamic measurements of cos theta. So this equation will be very, this measurement is very useful whenever we deal with the granulation, pelletization, okay, or coating, especially in pharmaceutical industries, because in those applications, because in these applications, the measurement of theta, or the wetting behavior of solid, is very important. Okay, so this is what going to be my final Washburn equation. We will try to look at this problem, that is the determination of heat of immersion based on the surface tension and contact angle data. So this is based on the application of Young-Dupré, which we derived in previous class, right? So in this problem, so some data have been given already. So we know what is the gamma LV, okay, and we also know the contact angle, right? So which is nothing but, the values have been given here, that is 22 millijoule per meter square and 30 degree, right? And the temperature data is also given here. And in addition to this, we also needed, the temperature variation, the data regarding the temperature variations of surface tension and cos theta. But the values have been given for both this, variable, that is nothing but minus 0.10 millijoule per meter square Kelvin and 0.0010 per Kelvin. So let's begin. So this is actually for the case of liquid alkane on Teflon. All right, so let's start with our equation, governing equation. So this is for delta H immersion. So you have first term is all about gamma cos theta. Second term is T cos theta, though the variation of gamma in T, and T gamma and variation of cos theta in T. So these data have been given. So let's plug in these values. The gamma LV is 22 millijoule and theta is 30. So we can see, so minus 22 into 10 power minus 3, right? So you can also, then cos 30, okay, plus we have temperature data, that is 293 into cos 30 again. The variation of gamma with respect to temperature is given, that is nothing but minus 0.10 into 10 power minus 3, right? Okay, that is also given. And the next term is plus, right? Next term is 293 into 22 into 10 power minus 3 into 0.0010. So that is the data which is given here, 0.0010. All right. So if you just do these things, so you will get, for this, you will get minus 19.05, plus the second term will be minus 25.374, plus for the third term you will have 6.446, right? So finally you will get the answer as minus 38 millijoule per meter square. So this is for delta H immersion, right? Okay. Or you can, so the answer for the heat of immersion for this problem is nothing but minus 38 millijoule per meter square. Okay. So I think this is based on the N2Pre application. I think by now we'll be able to understand how we can calculate heat of immersion, especially when you're dealing with the granulation and coating and pelletization and for those applications, right? And if you want to calculate what is the amount of heat released, okay, during the during those operations, right? Although one can measure through the microcalorimetry, maybe this method can be used to complement the calorimetry data. Okay, we will stop here. We will continue from the next lecture. Thank you.